In this lecture we're going to study a bunch of circuits that involve diodes. A lot of these circuits have capacitors in them, which we haven't really studied yet, but we just need to know that capacitors will store up charge and have a voltage across them. The first circuit we want to talk about is a circuit that makes an ideal diode out of a real diode, and we do that by using an op-amp. So first let's discuss what we mean by ideal. So consider this circuit where we want V out to equal V in, but only when V in is greater than 0. So we put a diode in there, and so if V in is greater than 0, then you would expect current to flow this way, and but you'll have a small diode drop here, but V out will be pretty much just a little bit less than V in. But if V in is negative, then V out should be 0 because it's connected to ground basically through the resistor. So how do we get rid of the diode drop? First, this is what the actual behavior is. We have this red line as the actual behavior, but what we want is the blue line here, right? So if V in is positive, V out is the same as V in, but we have a slight diode drop. So how do we fix that? Well, we can stick in an op-amp between V in and the diode, and then the diode is on the negative feedback part of the loop here. And so if V in is greater than 0, we know that the diode will try to use its negative feedback to make these two voltages the same, so V out has to be the same as V in, and we'll get the blue line coming here. Pretty much guaranteed. The feedback will be just so that the output of the op-amp compensates for the diode drop, so it must be a little bit above V out, but not by a noticeable amount. Well, it'll be noticeable if you look there. But so the problem, though, is if V in is negative, then we would try to follow going backwards, and the diode would cut off the negative feedback in that case, and there would be no negative feedback, which means there'd be a large voltage difference between the inputs, and it takes time for an op-amp to recover if there is a large voltage difference between its leads, if that voltage changes polarity. So we would like to avoid that. With a negative amplifier, rather than the voltage follower positive amplifier we looked at before, we can do better. So here's the behavior, as we've already learned, of a negative amplifier, right? So the input is proportional to the output but negative. The case I've drawn here is when R2 and R1 are the same. Imagine putting a diode in the feedback loop. Now when V in is negative, we have current flowing. The current has to be flowing this way, so the current flows out from the op-amp through the diode the right way, up, around, and back this way, so we get the op-amp with negative feedback, with a gain of 1 in this case, or whatever gain we want. We still have the case that if V in is positive, there's no way for the current to flow past the diode, but we can fix that by putting a diode here, and basically now if V in is positive, we will just bypass. The current will go like this, and V in and V out will be 0. So we can also, now if we want to have the diode working on the positive side, on the negative side rather than the positive side when it's off, we can just change the polarity of the diodes. Now if V in is negative, we'll just get current flowing this way, and we'll bypass it. If V in is positive, then the current flows this way. It can't go this way because it's blocking the diode, blocked by the diodes. But so the current can flow like this, and then V out can be the same as V in, or whatever the gain is. Of course, whatever we do on this side affects the thing. So if we're only looking for V in, we can move the point of this kink just by adding another source. This example that I've shown here, I've kept the two resistors the same. So if I add a bias voltage here, the balance of these two currents is where the 0 point is. So if I have 1 volt here, and then I have to balance this part to move the kink over. So this example, if I have -1 here, I have to have 1 here before I turn on the voltages, and therefore V out and V in will be all shifted by 1 volt to the positive. Okay, so that's how to make an ideal diode. What about the case where we want to do other things? So I'm going to describe a bunch of circuits now, the first of which is a clipping circuit. So here we want to get rid of part of the signal that's greater or less than some voltage. In this case, I'm going to show a voltage of at 0, and I've forgotten to draw in here a resistor limiting current, but I just draw it in there. So in this case, imagine that Vin is positive. What happens is that all the current will flow through the diode, and V out should be 0, or just actually the diode drop, since we don't have an ideal diode. So if we start with this kind of -12 to 12 input, the output, whenever we're greater than 0, will get clipped off. And let me put in my current limiting resistor there again. Right, all this part can't get transferred to V out. It all goes through the diode, and so the output just is stopped at that level. So we call that a clipping circuit. Clipping circuit has a diode connected to some voltage reference. Here it's 0. If we put a voltage source here, we could change the level of that clipping. We can also change the orientation of the diode, and now we clip the opposite half. So in this case, whenever Vin is less than 0, current flows here, and V out is just the diode drop, now with a negative sign. And again, we can put a voltage source in there to change that level. To show how we can use this, imagine this circuit where we start with Vin being a square wave going from -12 to +12. That's shown by the red line here. And I've used a voltage divider to cut that down so that this point here will be 5/12 of whatever this is. So this one goes from -5. This point would go from -5 to +5, except that if it wanted to go to -5, then current would flow here, and we get rid of this point. And so this point would be near to 0, or actually a diode drop below ground. So it would be a little bit, so minus 0.7 volts for a silicon diode. I run it through an inverter, a logic inverter, which takes that minus 0.7 and just says, oh, that's a 0, makes it 5 volts. And it takes the 5 volts and says, oh, that's a 1, makes it a 0, and I go exactly 5 volts to 0 volts. So basically the clipping part of the circuit gets me close to what I want, and then I clean it up with my digital inverter. Another thing I can do is make a signal and move it to some particular voltage with what's called a clamping circuit. Clamping here means I clamp one side of my alternating circuit to some voltage. So let me start with what the capacitor does here. Vin, if it is not centered around 0, will quickly charge up this capacitor to its average value, and therefore the output will only see the changes that come through. And that's shown here. If I start with minus 24 to 0 circuit, then sometimes it's minus 24, sometimes it's 0. When it's minus 24, a current flows and charge builds up here, so there's a voltage difference across the capacitor. Half the time that voltage difference would be minus 24, half the time it would be 0, and assuming that it can't respond quite fast enough to do both of those, it'll quickly charge up to plus 12 volts across this way, And so the minus 24 would go to minus 12, and the 0 would go to plus 12. And so if I start with the blue line here, minus 24 to 0, it quickly charges up so that it's halfway up, and so 0 is here, and we go minus 12 to plus 12. So now what happens if I put a capacitor, a diode here, is that whenever V out, so I can quickly draw charge this way if this is less than 0, but when this is greater than 0, I slowly flow out back on the resistor. Basically means that any the minus 24 here quickly makes this charge up to minus 24, but the plus side of this, when it's at 0, only slowly drains down this way. So that will put the bottom of my input at whatever voltage I set with the diode. So here I'm comparing to 0, and so I'll take my minus 24 to plus 24, or my to plus 0, or minus 12 to plus 12, and quickly put it at one diode drop below 0 to plus 24. So minus 0.7 to 23.3 in this particular case. And of course, if I change the direction of the diode, now I've taken this level and say, oh, the top of that signal can only be 0 or plus 0.7 volts. And so I take my plus or minus 12 and I make it to 0 to minus 24. So basically, depending on the direction of the diode, I clamp the bottom of the signal to 0, in this case, or whatever my reference voltage is, or the top to the reference voltage. Another detector now, I'm going to switch the roles of the capacitor and the diode. In this case, I have a V in here that is varying. Say it's a sine wave, so I can draw its as a function of time. It doesn't have to be a sine wave. It can be any odd function. And now I want to imagine what that does. So here V in is coming. It's going up. Current would flow through the diode as long as this node is lower in voltage than that. And the capacitor will charge up to whatever voltage it needs. So if current can flow, it quickly charges up the capacitor. But if this voltage is lower than the voltage across the capacitor, no current can flow backwards. And so what happens is that I have one diode drop down, and then so I follow my V in as it's going up. But once this point is higher than that, when V in is going down, there's nowhere for that charge to go. So this just comes along flat, and I keep following my input, but I never go down. And so therefore, V out will always be the peak value of V in that it can see. I can always put in a resistor here in parallel with the capacitor and slowly drain off that charge so that I can have the peak over the last so much time. Okay, so that brings us to rectifiers. Rectifiers are what we use to convert AC current to DC current because the current can only flow one way through the diode. And to really be accurate here, I should always put in a current limiting resistor. So imagine here I have an AC voltage source. So the voltage is going to change. Here I've drawn it going from plus or minus 5 volts, that's the blue line, with a frequency of 1 hertz. And when the voltage is positive, I can have current flowing around through the load resistor, and my output will be basically just the loss from the diode, and actually I don't need the currenting limiting resistor here because I have the load resistor to make sure that the voltage, the current has somewhere to go. So when the voltage is positive, I have the current flowing. I have a slight drop from here, so you see I have the diode drop on here. But when Vin is less than the diode drop, I can't get current to flow backwards, so I cut off that part of the signal, the negative part. Now, if I just look at that signal, it's very humpy with large sections. I can smooth it out at this level by adding a capacitor and a resistor here. The resistor and the capacitor, if you multiply their values together, you have something with units of time. And as long as I make that combined value much bigger than the time between peaks, then I'll get a fairly smooth value, and I'll get this kind of behavior. This is essentially a peak detector. As you see, it followed the peak and then it slowly decayed away. I followed the peak every time. Now, if we use both halves, all I have to do is put another diode in the return thing. Now I can get current going this way. Well, here I just put two diodes. They both work the same way. I get two diode drops. But now I need to have this pair work in the other direction as well. Here I show the other half. So now I only get the current going this way. And I get the other half of the set. I can combine those in what's called a full bridge rectifier. So you can see that if the current is positive, I go this way. I can come through this way, around, and back. Or when the voltage is negative, I can go this way. Notice that both those directions, this direction, down through the resistor, and this direction, I'm still going down through the resistor, so that I get both halves of the thing, of this cycle, going through the resistor in the same way. Now I have these, both halves of my signal going in, and I have to do less work with my RC coupling. So we call this a full bridge rectifier. Okay, one last thing. We haven't talked about Zener diodes, and all diodes will break down if there's too large a reverse bias. If we make the voltage on this side too much higher than that, it'll break down and current will flow this way. That's not good for most diodes, and what happens in these cases is that we get avalanches, just like the breakdown of air as an insulator. That is not good for most diodes, but there are diodes designed to break down at precise voltage, and those are called Zener diodes, and we put a little wings on the diode that sort of make a Z shape for the Zener. And so here I've drawn the IV characteristic for a Zener diode in the normal way, plus minus on the voltage drop, and if we put a large negative voltage, eventually, at something like 6 volts, we get a very sharp cutoff. Notice this cutoff is much sharper than the turn on of the regular diode. So the breakdown voltage works very much like a regular diode drop, but it cuts off at different values. So here I have a circuit, and we can see what happens. So I have V in going to V out. Notice that if I didn't have the diode, I have just a voltage divider, R1 over R2. And so if I put in voltage here, when V out is greater than 6 volts, this is a 6 volt Zener diode, and notice it's backwards. When this is greater than 6 volts, higher than ground, it'll force a voltage through. So I can't get V out more than 6. So here's my input. My output, when it gets to 6, cuts off. Now when V in is negative, it still works like a regular diode and current flows, and so V out can't be less than 0, and so I also cut off the bottom half. So I can make a circuit that clips two sides of the signal with the Zener diode.